I really liked the theme of uncharted waters. It made me think of this ostrich egg. Can we see it? No. This ostrich egg. The oldest surviving globe in the world. It was carved at some point around 1504. And somewhere around the southeast coast of India, the cartographer happened upon some uncharted waters. So he just engraved in Latin the phrase, "Here be dragons." Here be dragons, what does that mean? Is that a warning? Don't go here, stay away, there are dragons here. Or is it a recommendation? If you want to hang out with some dragons, this is where to go. I guess it depends on who's reading the map. You can either stay at home with a nice cup of tea, or you can go into uncharted waters and slay some dragons. Personally, I'd go for the dragons. Architecture is an act of exploration. As Eric Sanderson has shown us with his beautiful Manhattan project, yesterday's uncharted waters become tomorrow's gridded concrete jungles. This is his take on 400 years of the history of New York. The age of exploration, of course, is long gone by now. We've already mapped out all of the Earth's land masses and waters using either ostrich eggs or global satellite navigation technologies. It's easy to think that there are no uncharted waters left, no dragons to go and slay. And yet we know very little comparatively about the roughly 5 nonillion, that's a 5 followed by 30 zeros, of bacteria that are in the world around us. This biomass of bacteria is larger than that of all plants and all animals combined. The biomass is so large that it's almost wasted on us. It's so very abundant that we don't really know what to do with it. And this theme of waste runs through the history of humanity somehow. It's been pointed out by David Schiller that a typical coffee business uses something like 0.2% of the coffee bean, meaning that 99.8% of the coffee bush becomes waste. Then he added, Schiller, that what we don't understand, we can't possibly explain, value, or protect. Despite this context, it seems that a lot of contemporary architects don't seem very interested in the materiality of the profession, in the matter around us and how they come together into buildings. This is one of my old student projects. It's a laser-cut cardboard model, but that's not important. That doesn't really matter. The materiality of the object is irrelevant. It's just a representation of an underlying geometry. And it seems to me that we've become very good at scripting computers to produce these eye-catching forms for us, but that we've lost a bit of the material sensibility along the way. In the studio that I run from London together with my co-founding partner Alex Kaiser, we hold a different position than this. It's an architecture studio, but it's also a material laboratory where we test new ideas for what our buildings of the future might be made of. It needs to be a laboratory because we refuse to use ready-made solutions to new challenges. This picture of my desk might go a little bit of the way to show what I mean by laboratory. You can see a 3D printer, you can see some chemicals, a Bunsen burner, some material tests that we've cut on our CNC router, and crystal experiments growing in a jar. So why does this talk about matter really matter? I mean, what's the reasoning? It's because of the huge construction industry that we have, which is one of the largest users of resources, energy, materials, and water. We need to go beyond the commendable goals of the net zero movement. We need to start designing buildings that produce more energy than they consume. Instead of more passive houses, we need more active ones. Material considerations is an obvious starting point for this discussion. The story of human evolution is often told as that of a story of tool-making processes, but I think we can equally well view it as a story of humanity conquering new materials. We have the Stone Age leading on to the Copper Age, to the Bronze Age, to the Iron Age, and so on. Yet, the material palette that architects use is largely composed of the same elements that we've always used. It's brick, it's stone, it's metal, it's wood, it's plastic, it's glass, and it's concrete. So let's talk about concrete for a second. Both stigmatized and admired, this is arguably the most important building material on the planet today. It's got a 7,000-year-old long history, including the building of the Pantheon in Rome. Still to this day, the largest unreinforced concrete dome on the planet. In 1903, the 15-story Ingalls building in Cincinnati, Ohio, became the first reinforced concrete skyscraper. We could now build really tall with concrete. And this is just a mere 12 years after architecture enters the Steel Age with the Monadnock building in Chicago. Already we're in the concrete age. And then happens almost nothing. We're still stuck in the concrete age. Aesthetically, I don't have a problem with this. I like the look and feel of concrete as much as the next architect. It's just that I think we can produce our buildings in a smarter way than by burning limestone and clay at 1450 degrees Celsius, producing 1 ton of carbon dioxide for each ton of cement that we make. The only thing that we humans consume more of than water is concrete. We produce an astonishing cubic meter and a half of concrete, roughly 2.5 tons, per person on this planet every year. That's you, you, and you, and you, and you, all of you. A cubic meter and a half of concrete. However, material ages come to an end, and I think when we manage to break free of the concrete age, we will find ourselves in an updated timber age. And after that, I think we'll move into the Materiomic age. So let me show you some projects that we made, some buildings and cities that we've designed for these upcoming material ages. Let's begin with the soon-to-come timber age. And I'll show you 2 examples of skyscrapers made from wood that we've designed. We're already beginning to get a hint of this age. This is the Stadthaus building in London, just around the corner from where we are. It was done by Wall Thistleton Architects. And it's 9 stories tall, making it one of the tallest timber buildings on the planet. Yet, that's not very tall, is it? I mean, we're working now with timber engineers, and we're quite certain that we can go to 30 stories or taller. This is one of our wooden skyscrapers, Perch. Timber is the one commonly grown and therefore exceptionally renewable building material on the planet today. It also acts as a storage for carbon dioxide, so it seems to me that the more timber buildings we can make, the better. This is an interior view, and this is a night shot of it. So how can we make the built environment be composed of even more timber? Maybe through making an even bigger building. Arborea is a massive gridshell structure off of which entire buildings are hung. So we have this superstructure, and we plug in the houses into the superstructure, which only touches the ground in as few places as possible. It's a very large structure, a huge structure, with a very light touch. And it's also a new typology that is only made possible through the use of engineered timber materials, the very latest timber materials. Here's a later version of the same scheme where we're adopting a red and white color scheme that echoes that of the vernacular buildings in my native Sweden. This timber grid shell could dip down on land or into water. It would float above the ground. The grid shell itself would provide circulation walkways between the buildings, and it would make it possible to live in a building made from the forest, high above the forest. And the interior of the building would also be composed of as much timber as we can possibly get in there. So now we enter the Materiomic age, where we view material systems holistically. This is a neologism that I didn't make up myself. It's used primarily by some very smart people at the MIT. But in this emergent field, fundamental links between material processes, structures, and properties from the nano to the macro scale are examined using systematic, experimental, theoretical, and computational methods. So our first venture into this world of the Materiomic age is crystallia, based on the idea of growing crystals into buildings. So we had to go into a real laboratory to start doing this project. Not that I had a problem with that. I basically do anything to get into a white lab coat, or to look very serious while stirring some shockingly blue liquid in a beaker as it heats up. Working with a chemistry professor, we built these architecture models, growing them straight from crystals. We then tried other crystal types, investigated different ways of doing this process, made more models of crystallized buildings. Architecture through chemistry, buildings that drip into shape over time, like stalactites or stalagmites. An entire city, perhaps, of crystals that changes through chemical reactions, a city in constant flux. Maybe crystallia would hang off the cliff walls of a gorge with an artificial dam beneath it that we would seed with crystals that could then grow into buildings. Maybe some of those buildings would eventually melt back into the water and be reseeded and grown into new buildings. For our next Materiomic Age project, Arachnia, we wanted to try a material that really isn't readily available yet. So there's a competitive race going on between several companies at the moment to be the first to synthesize spider silk proteins into an artificial fiber material with remarkable mechanical properties. And we're thinking of using this to suspend an entire city above ground, maybe in an earthquake-prone area. Sadly, we're not going to see this project in real life anytime soon. I had a conversation with one of the representatives of one of those companies a while back, and he told me that we might be about 10 years away from being even remotely close to doing anything like this. And still, I quite like the idea of us designing with a material that might be available 10 years from now. There's something nice about that. The final projects are June and Sandra, both belonging to the Materiomic age. June is a 6,000-kilometer-long habitable wall stretching across the entire African continent. About the size of the Great Wall of China, it would not be made of concrete, but of particles that are invisible or near invisible to the naked eye, bacteria and grains of sand. A city made from biologically solidified sand, a new way of creating a very long and very narrow Pan-African metropolis. Dry areas cover more than 1/3 of Earth's land surfaces. Some of that is already desert, some of it is being seriously degraded by the shifting sands. So that's bad news, right? That's a negative thing because of desertification, because of the realities in these parts of the world. However, if we choose to look at it optimistically, we might view these sand dunes as ready-made buildings. And those buildings might be used to stop the sand from shifting. So all we need to do is solidify the sand dune where we need solid surfaces, and then excavate the sand that we don't need. Simple. Or we can have the wind excavated for us. So the wind carries the sand onto the site and then carries the redundant sand away from the structure. But how do you solidify a sand dune? How do you glue those grains of sand together? Maybe you use these guys, a microorganism called Bacillus pastori, readily available in wetlands and marshes, that have the remarkable capacity of solidifying loose sand. What happens when you pour these onto sand is that they start filling up the gaps in between the grains. And a chemical process then produces something called calcite, which is a bit like nature's own cement. And that cement binds the grains together. It takes about 24 hours for this cementation process to take place. And theoretically, we should be able to solidify a sand dune into a structurally sound building in about a week's time. So here I am, playing the part of the mad professor at UCL in London, growing some bacteria into bacterial sandstone. I told you about the white lab coat obsession, right? Sandra is the extension of Dune. Now we're looking really closely at the project on the city scale. So the buildings have become orthogonal to simplify the construction process, but they're still following the flowing forms of the sand dune. And the entire city of Sandra becomes an architectural anti-desertification device made from the desert itself. Sand-stopping buildings made from sand. All cities, of course, are essentially made of sand and rocks. It's just more obvious with the bacterial sandstone city of Sandra. The buildings would melt into the dunescape. In the daytime, narrow passages between the buildings would offer shaded walkways through the city, while at night, the interior courtyards would light up from within. So why do we design these seemingly impossible buildings and cities? Partly because we think they will be very possible very soon. Here's a person who's not afraid of uncharted waters, Chris Voigt, one of my science heroes. He's a synthetic biology professor at the MIT. And he's a bit of a hacker, but he doesn't hack computers. He hacks bacteria, reprogramming them to perform complex tasks. For one of his experiments, the living camera, he made bacteria run out and form this shape. Now, consider a 3D version of this 2D experiment. We could essentially 3D model a building on our computer and then program bacteria to run out into an aggregate material and form that same shape. We could then use the same method that we use for Dune and Sandra to solidify that aggregate within the material. So that would essentially be the same as programming a material, using tiny biological robots to construct our buildings within the material mass itself. That would be architecture in the Materiomic age. That's why I think synthetic biology and material sciences are the most interesting uncharted waters in architecture today. And if we have to slay some dragons to get there, so be it. Yassos.